Alright, here we are for the next video, 3.2. This is about water's important characteristics that it has. And there are four kind of important qualities that we're going to talk about when we talk about water. And those qualities are those those are essential for life to exist as it does on Earth, right? So we're going to talk about the fact that water is cohesive, adhesive, and it has a high surface tension as one kind of aspect of its characteristics. We're going to talk about the fact that water is great at moderating temperature or regulating temperature, so keeping temperature the same. And it also expands when it freezes, so it's less dense as a solid than it is as liquid, and also that it's an excellent solvent of all kinds of substances. Okay, so jumping right in, let's talk about cohesion. So you've probably heard the word cohesion used to describe all kinds of things, including maybe like group dynamic, like if people are cooperative, then they're cohesive, they stick together, right? But cohesion is simply a term to describe when stuff sticks to itself, okay? It's not sticking to other stuff, it's sticking to itself, right? So water turns out, as you probably already figured out, it sticks to itself very well. So if you have one water molecule, it is going to stick to another water molecule. And, you know, I could ask you right now, why is that the case? And you should be able to give me a resounding answer that it's because of, yes, hydrogen bonding, right? We talked about this, that we have our polar water molecule, we have our hydrogen, we have our oxygen, we have our hydrogen, and when it comes close to another hydrogen, oxygen, and hydrogen, then we see an attraction forming, and that is really important for water to exist as it does, right? So this hydrogen bonding that happens between water molecules allows water to stick together. And this is really important for water being able to go up against the pull of gravity, right? Because I mean, I don't know how many times you've looked at a tree and wondered to yourself, how does the water even get up there, right? Like, I can climb up there myself, right? And how does a water molecule climb up there? And one of the reasons why water molecules can do that so well is because of the fact that they have these hydrogen bonds and they have this cohesion, okay? And I'll have another diagram later on that will kind of show this more clearly. Another quality that water has is that it's adhesive, right? And so you've probably heard of adhesion in reference to maybe tape. Someone has talked about something being very adhesive, like tape being very adhesive, or not being adhesive if it does not stick, right? So adhesion is when stuff sticks to other stuff. If it has high adhesion, it sticks well. If it has low adhesion, it's not very sticky. Okay, so here we're talking about water molecules sticking to other substances. And again, it turns out that this is because of the fact that we have these hydrogen bonds, right? We have hydrogen, we have oxygen in the water molecule, and they form these wonderful hydrogen bonds with not just other water molecules, but other substances. And in particular, this is helpful for sticking to cell walls. And we haven't talked a lot about this, but maybe you remember it from your previous biology classes, but cells in plants, they don't just have a cell membrane, but they also have a cell wall. And that cell wall is made out of a lot of things, but including cellulose. Cellulose is just a complex carbohydrate that's made out of glucose. And glucose, I know this is kind of a long journey, is made out of carbon, hydrogen, and oxygen. Okay? Just a bunch of carbon, hydrogen, and oxygen. And so that oxygen and that hydrogen is going to be able to form those wonderful hydrogen bonds that we saw between water molecules, right? And so that's why we see that water sticks really well to a lot of different types of surfaces, is because of the hydrogen bonding that it forms. And I'll have a diagram later on that explains this a little bit more. But here we have a photo, right, and you see these water molecules, or these water droplets, and they're sticking to the surface of this leaf, even though some of them are at an angle, right? And that has to do with the fact that it's sticky. Water will form bonds, it will stick to substances other than itself, and it does this well. And that again is helpful in trees getting water up to high parts of them, or plants too as well. So here we have a diagram, and hopefully this clarifies it a little bit. So if we look at the roots of a tree, right, that's where the water, most of the water is being taken up, although it can be taken up through the leaves or other parts of the tree. But in the roots there's a lot of water absorption, right? And so we see the water molecules and they're flowing into our root, and those water molecules are sticking together. And you might think about that as if they're holding hands, right? They have the hydrogen bonds that form between them, and those are holding them together, right? And so those water molecules are kind of pulling each other along because of this cohesive property that they have, right? But they're sticking to the sides of whatever channels they're going through, whatever cells they're going through, right? So they're forming these hydrogen bonds to whatever surfaces they're getting into contact with, right? So they're adhesing. They are adhesive when it comes to the surfaces that they're going through. And so they're sticking to each other, they're sticking to what is around them, and they are slowly able to then climb up very well. And so we didn't talk about this so far, but there's also there's sort of like this water gradient. There's this difference in water concentration, or in like the abundance of water at the roots of the tree, at the roots in the cells that are at the roots of the tree, versus the ones that are at the top of the tree, or whatever plant we're talking about. In this case, it's a tree. And there's a high concentration of water that's at the base of the tree, right? That's where the source of the water is. And as this water gets pulled up, it's cohesive, it's adhesive, but it's also being pulled up because of this potential gradient that exists. Because there's a low concentration of water higher up, there's a higher concentration of water lower down, and so there's a force that pushes the water up. And so the water molecules are sticking together, they're sticking to the sides of whatever channels or cells they're going through, and there's also a force that's pushing them slowly up. And part of that has to do with the fact that plants sweat, essentially. We call it transpire or transpiration. And so the leaves of cells will let out some water because they have these pores that allow them to do that. And as water is being lost to the atmosphere, then more water is being pulled up. And so it's this kind of like entire gradient that pulls the water all the way up through the tree. And we'll get into more depth about that later, but the important thing to remember is if it was not for the fact that water is cohesive and adhesive, this would not work as well. Okay, so it's really important that water has those properties. There's one more property that I want to talk about with you, is this idea of surface tension. So you need to know that water has a high surface tension. And what surface tension is it's just the measure of how hard it is to stretch or to break the surface of something. So, for example, if you have a water droplet on a surface, then it will make this wonderful kind of spherical surface. And that has to do with the fact that those water molecules are arranging themselves. They're bonding with each other at these hydrogen bonds in a way so they kind of stick together. They're not just, sticking to each other and the surface that they're on, but they stick together to create a very hard surface to break. And when I say very hard, I mean compared to other liquids. Obviously, it's not like a solid, but compared to other liquids, it's definitely harder to break. So for example, if you took ethanol, that's always something that we like to compare water to, if you were to spill some ethanol on a surface, you wouldn't see the same kind of beating happening. In fact, you would see probably it just spreading out very quickly. Whereas water might bead up a little bit and then spread out, and that has to do with its surface tension. And so that's useful for a variety of reasons, including the fact that some organisms can live on top of water, and it makes really beautiful water droplets. So moving on to the next quality. So that's surface tension, cohesion, and adhesion. Now let's talk about water regulating temperature. So if you look at coastal regions, you'll see that the temperature on the coast is much more regular than you might get inland. And a lot of that has to do with the fact that there's so much water around it. So before we jump into the nuances of the water regulating temperature, I want to talk a little bit about energy and heat and temperature. So when we talk about temperature, we talk about kinetic energy. And kinetic energy is just the energy of movement, right? It's the energy when molecules are moving we refer to them as having high or low kinetic energy. If they have high kinetic energy, then they're moving very fast. If they have low kinetic energy, they might just be vibrating a little bit, okay? And we can also talk about heat as a form of energy, right? And so when you heat something, when you add heat to a particular sample, what turns out is that you are increasing the kinetic energy. So it has more kinetic energy, the molecules are moving faster and faster and faster, and as that happens, as the kinetic energy increases and your molecules are moving around faster because it's getting hotter and hotter, the temperature will also change. And so what you need to know for temperature is that temperature is simply a measure of the average kinetic energy. So if you have a sample of something, let's say it's a sample of water, let's say it's a cup of tea maybe even, right? When you take the temperature of that water with our thermometer, that's a thermometer, what you're measuring there is actually the kinetic energy of that sample, the average kinetic energy, right? Like on average, how much kinetic energy does a given molecule in my sample have, or an atom, whatever you're talking about there, right? And so that is what temperature is a measure of. And we have a few units of measure for that, right? So when we measure temperature, we measure it in degrees Celsius when it comes to science. You may have come across it as Fahrenheit in just like everyday life, but in science we always talk about the Celsius scale as our measure of temperature, right? And we can talk about the temperature of water. We can say water freezes at 0 degrees Celsius, it boils at 100 degrees Celsius. I would recommend that you memorize those numbers. They're not too hard to memorize. Maybe you already have memorized them, but it's good to know that water is a solid, or it turns into solid at 0 degrees Celsius, and it turns into a gas from a liquid at 100 degrees Celsius, right? So temperature is one aspect of water that we can talk about, or one aspect of heat that we can talk about, but we can also talk about the amount of heat that's needed to change the temperature of something, right? And when we talk about that, we talk about calories. And these aren't exactly like the calories that you come across when you look at the food labels on like a candy bar that you eat or on whatever you're eating, but they are very much related, and we'll get into which one exactly we're talking about here. So calories are a measure of energy, right? And calorie, 1 calorie with a lowercase c, is the amount of heat, the amount of energy that is needed to increase 1 gram of water. So if I have 1 gram of water right here, to increase its temperature by, no, that's an arrow that's saying increase. Did not do a good job with that. Let's try again. To increase temperature by 1 degree Celsius, right? So if my 1 gram of water here is 4 degrees Celsius, if I want to change this temperature to 5 degrees Celsius, I would need 1 calorie of energy. And this is just a unit of measure, right? This is how we measure our energy. However, it's not that simple. We can also talk about calories. So since this calorie with a lowercase c is not a lot of energy, we oftentimes talk about kilocalories, right? And remember that kilo simply means 1,000, right? So a kilocalorie, or a lowercase k with a lowercase c a l, is 1,000 lowercase c calories, which actually is the same as 1 uppercase c calorie. I'm not sure who came up with this, but they were not thinking about the fact that it's going to be really confusing for everyone to learn. But that's how it is in science. Sometimes confusing things are chosen. So 1 uppercase c calorie is the same as 1,000 lowercase c calories. You just have to memorize that. So we can talk about heat, and we can talk about energy in terms of calories. We can also talk about it in terms of joules. And so we can have 1 joule, and that's equivalent to 0.23 calories, or you can flip it around the other way, 4.18 joules is equal to 1 calorie. Okay, and you're probably going to come across both of those in calculations. I don't think you need to memorize these numbers, but you just don't be thrown off when you see a joule. That is just a measure of energy. So when we talk about water, we can talk about its specific heat. We can talk about the amount of heat that needs to be absorbed by a given amount of water to change its temperature, right? And so specific heat is a term that we use to describe the amount of heat, the amount of energy that needs to be absorbed or put it into whatever we're talking about here to change the temperature by 1 degree Celsius, right? And I just told you that we have water it needs 1 calorie to increase its temperature by 1 degree Celsius, right? And so that is the specific heat of water, and we write that as 1 cal per gram degree Celsius, okay? That means 1 calorie to increase 1 gram of water by 1 degree Celsius, okay? And compared to other liquids, that's actually quite a bit. Like, that's a high specific heat compared to other substances. So if we look at another substance that I compared before, ethanol, it turns out that only needs 0.6 calories, right? So it needs like almost half the amount of energy to increase its temperature by 1 degree Celsius if you had just 1 gram of it. And so these are units of measure, and we can talk about them in terms of 1 gram, but we can also multiply these out to larger amounts, okay? And so if I were to ask you right now, well, gee, why does water need so much more energy to change its temperature? You should be able to actually answer that yourself because it's been the same answer across the board. It's because of the hydrogen bonds, right? So if you want to heat up water and you want to change its temperature so that the water molecules have more kinetic energy and they're moving around faster, right? Then you have to first break apart the hydrogen bonds that are forming between these molecules, right? And so you need to put in energy to break the hydrogen bonds. You have to give enough energy into your given sample of water to kind of disrupt those bonds so that then those water molecules can start moving around faster. And when they start moving around faster, that's when we see the temperature changing. Okay, so the water's high specific heat is related to hydrogen bonds because the heat absorbed first breaks our hydrogen bonds, and then that heat can be used to change the temperature. Okay, so that's why water has a high specific heat, and that's really important for water because when we have an aquatic environment, when we have a lake, when we have an ocean, a sea, what have you, a river, a lot of times organisms need a pretty regular temperature, and living in water allows them to maintain their temperature and it doesn't change as much. We can also talk about the energy that it takes for water to change states, and that's pretty important as well. And so as you imagine, again, water has a relatively high heat of vaporization. And you might be wondering, well, what's heat of vaporization? It's exactly what it sounds like it is, right? It's the amount of energy that's needed to turn something from a liquid into a vapor, into a gas, right? So it's the amount of energy that would have to be absorbed to change a liquid to a gas. And when we look at water, again, it has a relatively high heat of vaporization. You need 580 calories just to take 1 gram of water from a liquid at 25 degrees Celsius to a gas. Okay? And that's 1 gram, right? And how often do we talk about 1 gram? We can talk about 500 grams of water, right? So water has this property that when you're trying to go from being a liquid, right, it's going to get hotter and hotter and hotter and hotter, and that takes quite a while. But then you also have a long time while it's still liquid, and then it's changing into a gas, and that has to do with the fact that it has a high heat of vaporization, which again has to do with the fact that it has hydrogen bonds. Okay, that's kind of all I wanted to talk about here. So those are the first two properties of water, right? We talked about cohesion, adhesion, surface tension, and now we talked about the fact that water is good at regulating temperature because it needs a lot of energy to be put into it before it changes its temperature. And that is very important for life sustaining on Earth. And it also is true for the other way around, right? So water needs a lot of energy being put into it for its temperature to change, but it also can lose quite a bit of energy before its temperature will decrease. So hopefully that's clear to you guys now. So let's talk about our third property here, the fact that water is less dense as a solid than it is as a liquid, which is wonderful and amazing and kind of exciting. So normally, when we talk about solids, liquids, and gases, I have this wonderful diagram here ready to go. When we talk about solids, we can talk about the atoms or the particles, whatever it's made out of, whether it's molecules, whether it's compounds, whatever, that they're very kind of close together and they don't have a lot of motion to them. They are vibrating to some degree, depending on their temperature, but they are close together and they are not changing their shape, right? Solids don't change shape or volume very much. They're not expanding, right? Like if I pick up my solid cup, right, and I put it somewhere else, its shape is the same. It's a solid, right? Whereas liquids, if you change the container that they're in, then they will change their shape. If I take, a water container that has this particular shape and I transfer it to a different container, then my water is going to change its shape. And that has to do with the fact that the particles that make up your liquid kind of are moving past each other and they're a little bit more spread out usually, right? And then we can talk about a gas, and in a gas it's a totally different game, right? You have particles that can expand, they can contract, and they can move around really fast, and they have very little attraction between them, right? And this is like kind of our normal paradigm, where our solid is the most dense, things are kind of the closest together, the particles are packed closest together, right? And in our gas, they're the least dense. But that is not the case for water, in the least bit. When it comes to water, our solid, our ice, is less dense than our liquid, right? And we can look at these diagrams and we see it. These water molecules are pretty close together, right? They're zooming around. They have their little hydrogen bonds that are next to them, right? Those bonds are breaking and they're reforming, but they're kind of close together. And if we look at the solid here, our water molecules are much more spread out, and they're actually spread out in a very regular crystalline way. And the reason why those water molecules will do that is, again, surprise, surprise, due to the hydrogen bonds that form between them. So when water freezes, the molecules, each molecule of water is actually aligning itself so that it forms this wonderful hydrogen bond with another water molecule that's nearby. And it does this in a very regular way. And what happens is that you get these big empty spaces between the water molecules, which results in it being less dense. And when it's less dense than the liquid, then we know that it floats, okay? Because when something is less dense than the substance that it's in, then it floats, right? And so our water, when it's in solid state, when it's ice, it floats, which is wonderful and amazing. For animals that need to live in aqueous environments where water freezes, because then they can, you can have like a lake and like the top of the lake can be frozen over, but you can still have your like little fishies underneath there living their happy lives if the temperature is not too cold. So that's the third quality of water that I want to talk about. And the last one that I want to talk about is the fact that water is a great solvent. And in order to talk about solvents, we need to go over these really annoyingly similar and hard to remember terms that for some reason someone decided was a really great idea to use. So when we talk about solutions, there are two parts to a solution, but before we talk about that, we should talk about what a solution is, which you should know. From your chemistry class, a solution is our homogeneous mixture of two or more substances, right? Homogeneous meaning that it's the same throughout. So you have your solution, it doesn't have any like big chunks of anything floating around in it. All of the parts of it kind of have the same characteristics, right? So what I just drew here is not homogeneous because it has chunks of something that's floating in it. But a good example of a homogeneous mixture right here is our sweet copper sulfate, CuSO4, solution here, because we can see that we have a solution and it's the same throughout. It's all this wonderful kind of teal blue color, right? And it's a mixture of our solvent and our solute, which in this case our solute is copper sulfate and our solvent is water, right? And just to go over it, A solvent is the substance that does the dissolving, right? It is our dissolving agent. It's what causes our solute to dissolve. Usually it's just what you have more of, right? Usually you have a larger amount of water than you do of whatever you're dissolving, or you have more of the ethanol, or whatever your solvent is. In biology, our solvent is almost always water, but it can be a variety of other substances. Then we have our solute, which is a substance that is being dissolved, right? So that is your salt, that is your sugar, that is your sodium, that's your copper sulfate, whatever is the substance that was usually in a solid form, not always, that was then put into the solvent, mixed up to make your solution, okay? And it's usually what you have less of, okay? So solution, solvent, solute, just memorize them, they're really annoying. So water is a wonderful and amazing solvent. Water can dissolve all kinds of things. It's really good at dissolving ionic compounds because they have a positive and they have a negative end, but in general, water is good at dissolving polar substances. So whenever you have a substance that has some kind of a positive end or positive side to it and a negative side to it, or sides, it can be multiple sides, then water is really great at dissolving, because what happens is that you see the water molecule will kind of float over, get close to whatever you're trying to dissolve, and if, let's say, this part of it that it's trying to dissolve away is a positively charged part of your substance, then the water molecule can angle itself so its negative side is right next to it, and it will kind of pull that part of your substance away, and that's what dissolving is. It's a breaking up of a particular substance, and so water is really good at breaking things up, because it doesn't matter if it has a positive side or if it has a negative side. Water can have both of those sides attach, because it has its slightly negative oxygen and slightly positive hydrogens, and so they will just kind of latch on to your substance until they pull it apart, right? And you can't really see that very well here. That's what's going on here. You have your negative side of the water molecule forming a bond and kind of like attracting the positive side of this particular protein that we have as an example, and then that protein also has a negative part to it, and so the water is kind of angling itself, so its positive side is forming an attraction with that part of our protein. And so what we see water doing sometimes when we have a large molecule that has many parts to it and some that are positive or slightly negative, they form this hydration shell, right? So the water molecules kind of just like stick to it and gradually pull it apart. Or sometimes they don't pull it apart, sometimes they just kind of like help it become part of the aqueous solution. And that is why water is such a versatile solvent. So it can dissolve all kinds of things, not just simple ionic compounds, but large polar proteins as well. And that's really important for life. Okay. Then we have two really fun words that you need to learn about water. And we can talk about substances as as being hydrophilic or as hydrophobic. And let's start with phobic, because you might be more familiar with that one. When we talk about someone having a phobia of something, they have a fear of it or a dislike for it, or they kind of have, they like to stay away from it, right? And so hydro is again referring to water. So substances that do not have an affinity for water, that do not mix well with water, that don't really form bonds with water, we refer to those as hydrophobic, right? Because they don't have an affinity for water. And a classic example of that is oil, right? You take oil, you mix it with water, you can sit there all day stirring it. It's not going to dissolve in the water, it's not going to mix with water because it's hydrophobic. It has no real affinity for the water. On the flip side, we can talk about water, philic substances that have an affinity for water, right? And so a lot of times those are ionic compounds. Those are polar compounds that are polar substances. And a classic ionic example of that would be sodium chloride, right? or other salts, I guess. So your water molecules get close, they find the anion, they attach their positively charged hydrogen ions to those anions, and then they will slowly kind of pull it apart and dissolve it, and it will become kind of distributed in your aqueous solution, right? And that's because it's hydrophilic and it has an attraction, has an affinity for water. Okay, so we can like classify substances as hydrophobic or as hydrophilic. A lot of times you'll see oils or hydrocarbons as being hydrophobic. They don't dissolve very well in water, but then you can talk about all kinds of ionic compounds as well as polar compounds or molecules like proteins having hydrophilic parts to them. And we'll talk about hydrophobic and hydrophilic when we talk about cell membranes, because it's actually these characteristics of the parts of a cell membrane that allow it to exist as it does. But more about that later. So just to recap, those were the 4 characteristics of water that we talked about. Water can be cohesive, or is very cohesive, adhesive, and has a high surface tension, all because of hydrogen bonds, right? Water is great at regulating temperature. It can absorb a lot of energy, but not change its temperature. And on the flip side, that's true as well. It can lose energy, but still keep the same temperature, for more so than other substances. We also see that water is less dense as a solid than it is as a liquid, and water is a fabulous and amazing solvent, and it will dissolve all kinds of wonderful things, which is really great for life. So that's the main part about water. And since we talked about water, we're going to talk about aqueous solutions. And so this part, it's going to be confusing. I'm going to go through it and I'll try to be as clear as I can be. But know that this part is going to take a while to settle in, and also that you're going to talk about it more in chemistry, and hopefully then it will make more sense when you grapple with it more. But just try to pay attention, then ask me questions if you have them, and I will try my best to answer them. So when we talk about solutions, we can talk about aqueous solutions, right? Solutions where water is the solvent. And when we talk about solutions, we love to talk about their concentrations. And when we talk about concentration, I don't mean focusing on things, and I'm not referring to your orange juice specifically, but actually that is related to the I don't know if you've seen an orange juice container that has concentrate on it. But concentration just means how much of something is dissolved in your solvent, right? High concentration is a lot is dissolved, low concentration, a little bit is dissolved, right? I'm sure you guys have all made like Tang or Kool-Aid, right? And you always have, you can make it very high concentration by putting like a lot of the Tang in it and a very little bit of water, or you can make it low concentration with just a little bit and it's like really watery and it's really gross. I guess both extremes are gross. You want to get it just right, right? So the concentration is just how much of something is dissolved. And the reason why we like to talk about it in biology is because when we talk about reaction, when we talk about chemical reactions in living organisms, or any chemical reaction for that matter, in order for a reaction to take place, molecules or particles or whatever we're talking about have to collide, right? And they have to collide with the right amount of energy in the correct position, but the important thing is they have to bump into each other, right? And if you have a lot of a given particle in your solution, then it's more likely that it's going to bump into something else. If you have a little bit, it's less likely to bump into something. And so we can talk about concentrations to help us determine how likely a chemical reaction is to take place. Okay? So we do all kinds of measurements for concentration. So I'm going to go over a few concepts that help us look at concentration. And the first concept is this concept of molecular mass, right? And so just like the name says, like it is the mass of a molecule, right? It's not the mass of an atom, right? Like we talked about atomic mass before. This is the molecular mass. So it's the sum of the masses of all the atoms in our molecule, okay? So here we have our sucrose molecule, which is made out of a bunch of carbon, hydrogen, and oxygen. And And we could count up how many carbon atoms are here, we could count up how many oxygen atoms are here, and then we could add up all of the masses of all of the atoms that are here, and we could figure out what the molecular mass is of our substance, right? That seems like it would be a lot of work, so I'm just going to skip to the example. It's a lot easier. Of sodium chloride, which is only made out of 2 different types of atoms, right? It's made out of a sodium and it's made out of a chlorine. And sodium has a mass of about 23 atomic mass units. Chlorine has a mass of about 35.5 atomic mass units, right? We add that together and we get 58.5 atomic mass units. So if we had 1 atom of sodium chloride, then it would have a mass of 58.5 atomic mass units, right? That's pretty straightforward. I'm going to come back to this. Just remember this part. We did this so far. We talked about the molecular mass so far, okay? Now, here's where it gets more confusing. We're going to talk about moles, but when I talk about moles, I'm not talking about the small fuzzy animal, the little mammal that lives in the hole that like doesn't see very well. I'm talking about moles as a measure of amount, right? It's how much of something you have. And a good comparison is the dozen, right? So when you have 1 dozen of something, maybe you've heard of this term, maybe you haven't. I hope you have. But 1 dozen means 12 of something, right? It's usually donuts. We usually talk about a dozen donuts or a dozen bagels. But you can talk about a dozen anything. You can talk about a dozen people. You could talk about a dozen puppies. You could talk about a dozen cell phones. Like, it doesn't matter what it is. The word dozen means 12, okay? And it's a word that we use to describe an amount. We, in chemistry and biology, I guess in science in general, we have a fabulous word to describe an amount of anything. I mean, I wrote here molecules, but it could be any particle. And this number is 6.02 times 10 to the power of 23. And I can rewrite that so you can see it. So 10 to the power of 23. Okay, this is an exponent. And so that's a huge number. We use this scientific notation so we don't have to spend like 2 minutes at a time drawing it all out. But, okay, maybe not 2 minutes. I'm going to just draw it out now for you. 602, right? And then we have a bunch of zeros afterwards. My commas are a little bit confusing. These are all commas, okay? Right? 1, 2, 3, 4, 5, 6. Okay. So this is 1 mole, right? And it could be 1 mole of hydrogen atoms. It could be 1 mole of puppies. It could be 1 mole of donuts. Even though that'd be really that would be a large amount of donuts, and puppies for that matter. So the reason why we use this number when we talk about about chemicals is because molecules or particles that make up a lot of substances are really, 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 really tiny. So it turns out this many, like let's say salt compounds, it's not that much. It doesn't take up that much space. In fact, in this diagram here, we have a container of sodium chloride that shows 1 mole of sodium chloride, right? And it's actually, you know, not a lot of salt. It's just like this small beaker. It's, you know, a beaker that's maybe this big. I don't know how you can see that. Of salt. And it turns out for sodium chloride, for NaCl, 1 mole, this many of those respective salt molecules, weighs 58.5 grams. And now hopefully you're like, wait a minute, I saw that number just now. And that's because you did, because that was when we calculated the molecular mass of salt. So when you calculate the molecular mass of something, right, when you do that calculation of the mass of each one of the respective parts of your compound or of your molecule, then you are actually calculating in grams, not atomic mass units, you change it to grams, how many grams it would take to have 1 mole of something, right? So when you add that up and you make your calculation of the molecular mass and you change the unit to grams, that is how much 1 mole of that substance weighs, right? So if I wanted to have 1 mole of NaCl, I wouldn't sit down and like count up like individually the salt molecules. Like you wouldn't be able to do that. Instead, we weigh a certain amount, and we know that is 1 mole. Okay, and yeah, maybe that blows your mind. Kind of blows my mind too. But you just have to learn that. You have to memorize that. So let's do an example. So if we have our NaCl, and I have, let's say I have 2 moles of it, right? And I want to know how many molecules of NaCl are in these 2 moles, right? Well, I know if I had 1 mole, it would be how many? I hope you said 6.02 times 10 to the power of 23 NaCl molecules. And if I have 2 moles, it's just times that number times 2. Right, and we multiply that by 2, we get 12.04 times 10 to the power of 23 molecules, which we could also convert to 1.204 times 10 to the power of 24 molecules. Right, so it's a lot. It's a lot of molecules. So there's one more thing that we need to talk about here when we talk about moles, and that is molarity. And so we can talk about the number of moles of something we have, but in particular when we talk about solutions, we want to talk about how many moles are dissolved in a given solution. And so we use a term to describe that. Instead of talking about concentration and saying something is high concentration or low concentration, I mean, we can talk about that as well, but we can also use the term molarity. And the molarity is a measure of the number of moles that we have of a particular solute, let's say it's still NaCl in this case, in a liter of solution. So it's saying, hypothetically speaking, imagine you have 1 liter of salt solution, right? So you have NaCl that's dissolved in water. If you have 1 liter of it, how many moles do you have, right? And you can have, you can have different molarity, right? If I only took 1 mole of NaCl, right? So if I took 58.5 grams and I dissolved it in 1 liter of water, I would have 1 molar solution, right? And this M we've used to describe the molarity, and we say 1 molar as our solution. But I could have totally taken a different amount, right? Like I could have been like, no man, I'm going to dissolve my, 2 moles of NaCl in 1 liter of water, right? And now I would have not a 1 molar solution, but I would have a 2 molar solution, right? And so you can imagine that you can have low concentration stuff that have a low molarity, and you can have a high concentration solution, so it has a high molarity. Okay? And we can talk about the molarity of different solutions, and you'll have questions where they say, something has a molarity of, 2 molar, or it's a 2 molar solution, how many moles of your solute are dissolved in it? They're probably going to be a lot harder questions than that, but that's a hypothetical easy question that you would get. Like this hypothetical easy question, right? So if we have some sucrose, and we dissolve 3 moles of sucrose into 1 liter of water, the question is, what is the molarity, right? And you can pause the video and do the math, but you really don't need to pause the video because you can just look at that and say it's 3 molar, right? Your solution is 3 molar if you have 3 moles in 1 liter. This question could have been a lot different, or maybe not a lot different, but a little bit different. We don't always say 1 liter. I could have said in 0.25 liters, right? And then you would just do the same thing. You do 3 moles, and you divide that by 0.25 liters. You always have to make sure that this one's liters in the bottom, and then you would get 12 molar. Okay? So these calculations are pretty fun and exciting once you get the swing of them. They're really frustrating until you do. Let's do one more that's a little bit more challenging. That's an example of something that you would come across maybe on the test. And I think this is actually one of your example questions. So in these types of questions, a lot of the times they're going to throw you off or try to throw you off by being like, oh, you know, this hormone and this metabolic pathway and all these things that you might not know about, right? But ignore that. Focus on the important stuff. We're talking about concentration here, and they give you a molarity. Oh, dang it. I should have corrected that typo. Anyways, I'll get to it. I'll correct my typo as I talk. So if we, in this question, we're talking about ghrelin, which is an appetite regulating hormone, right? It's a hormone that's released to help you recognize when you're hungry or when you're full. I'm not sure which one it is. But it doesn't matter, actually, for this question. But they're asking you if a person has a concentration of ghrelin in their blood that is 1.3 times 10 to the power of negative 10 molar. I didn't write the negative and I just wrote it now. It's negative 10, right? So if a person has this concentration of ghrelin in their blood, they want to know how many molecules of ghrelin are in in 1 liter of this person's blood, right? So if you took a liter of this person's blood, which I don't know, I guess you could. They're fasting. That's not a very nice thing to do to them. But if you took their blood and you took out 1 liter of it, so that's 1 liter of this person's blood, they want to know how many of these molecules are in it, right? And so you can use Avogadro's number to help you figure that out. So pause the video, try to grapple with it, and then I'll explain it. Hopefully you took a moment to try to solve this problem. Here goes. So our concentration is 1.3 times 10 to the power of negative 10, right? And we know that's negative 10 moles per liter. Okay, because that's what that capital N molar means, right? And so we know that we have 1 liter of blood that we're looking at, right? So those liters will cancel, right? This is 1 liter, 1 liter. And so I know, and I didn't even have to do that math, but you can if you want to, that I have 1.3 times 10 to the power of negative 10 moles of this particular hormone if I took 1 liter, right? So if I just took out the solute, if I just took out this hormone, I would have this many moles of it, right? But we need to convert that to the number of molecules, so we need to use Avogadro's number, which I guess I didn't tell you was what we call that number, but 6.02 times 10 to the power of 23 is also called Avogadro's number, named after some dude, Avogadro. Anyways, so I know that if I had 1 mole, I would have 6.02 times 10 to the power of 23 molecules, right? But I have less. I have 10 to the power of negative 10, essentially. Okay, so I have to multiply my number of moles times this Avogadro's number, right? So I'm going to erase this to give myself some space. I will take this. So I have 1.3 times 10 to the power of negative 10 moles times 6.02 times 10 to the power of 23. And I can do something here to help me keep track of my units. I know that 6.02 times 10 to the power of 23 molecules are in 1 mole of anything. It doesn't matter what it is, but in this case, it would be of ghrelin, right? And so I can cancel my moles because this mole is on the top, this one's on the bottom, and I multiply this out, and my calculator is is over here. Wow, I should, well, anyways, ignoring all the writing, the important thing here is that I'm using Wolfram Alpha. I don't know if you ever used it before, but it's a sweet calculator on the interwebs, and I just popped my equation into the search bar up here. 1.3 E, this capital E means 10 to the power of, so negative 10 times, parentheses 6.02, E, again 10 to the power of 23, and that gives me a number that you can't see. Let me erase it and make it, you know what, fuck it. Okay, we're just going to do it this way. Here is our answer, right? So it's a really big number, And if you want to convert that into scientific notation, for some reason it's not showing up on this one, but I did it actually through Google as well. Both ways work, but it's 7.8 times 10 to the power of 13 is our answer. So you can either write out all these zeros, but you should be also comfortable with this idea of scientific notation. And so that is the number of these ghrelin hormone molecules that we have. Okay, so I think that's all I want to talk to you guys about. So I'm going to give you guys more practice with these kinds of calculations because they can kind of be a headache, but don't be scared of them. You just got to use the concentration, Avogadro's number, and molar mass, and you can just convert between them. So we'll practice that more. That's all for now. Good job watching this super long video. Let me know if you have questions. Email me, leave comments, text me, call me, see me at school, all of the above. All right, have a good night. Bye.